Right. Okay. So the particle in a box is a very useful situation. Um, uh, Solving the Schrodinger wave equation gets wave functions that are in the form of a sine function, and we get a value for the energy, we get a value for the K, and we can combine those together to know how to calculate our energy levels. And of course, then we can calculate the absorption of those molecules. Okay, right. So what I wanted to do today is go from a situation where you've got a particle in a box to a case where you've got a particle in a potential. Okay, so I'll discuss a particle in a potential, but I want to tell you where I'm heading to. I'm trying to head towards diatomic molecules. So really, I'm trying to head towards a situation like that. But of course, my discussion is just of a single particle to start off with that is maybe attached to a wall with a spring, and its harmonic potential will, of course, be this half kx squared that we saw from molecular mechanics as before. So the problem with vibrational motion is that the moment you have a particle that's not perfectly free to move, this v term is not zero, and so we have to add a little bit to it. So the Schrodinger wave equation for particle in a potential is slightly more complicated. So the potential that a particle will receive is a half kx squared, where x is the displacement squared, half kx squared. So if we place that potential into the Hamiltonian operator and we have it there, then the Schrodinger equation looks like this. And of course, now this whole lot that we've got there must not damage psi. So solving this is a little bit more complicated, and it's beyond the scope of this course that we would try and solve it. But I'll show you what the results are. I've just seen a question now. How does the potential energy look? How does a potential energy look like a kinetic energy equation? Well, they're both quadratics. Okay, so the potential for a spring is a quadratic term. And of course, kinetic energy, half mv squared, is also a quadratic term. So kinetic energy, of course, you've got mass and velocity squared, and potential, you've got a force constant times the displacement squared. That's a very interesting question and a good question, because remember the equipartition theorem, where the energy of particles that can move in 3 dimensions is simply 3k. So remember back to there where the quadratic contributions to energy, quadratic contributions to energy all have a contribution. So please have a look back on the previous slides at that theorem. It's really important of the quadratic contributions. Okay. Now, this is what the Schrodinger wave equation looks like for a particle that is in a potential, a single particle in a potential. And the question is, what happens when you solve it? And a lot of interesting things happened when you solve it. So let's just start with it. Here's the Schrodinger wave equation. You end up getting a solution, and it's interesting that in the solution, this the wave function that you get for the solution, the energy of the different energy levels, the energy levels are equally spaced apart in the result. You'll remember that when we did particle in a box, that the energy levels start off quite far and they get a little bit close together as you go up. But it's interesting that the moment you have a potential there, your energy levels are equally spaced. So these energy levels are going up equally spaced, and you'll notice that there is a lowest energy level And if you want to see where the particle is, you're going to have to square the wave function so it looks like this. So at your lowest energy level, you will have the particle spending a lot of time, high probability, right in the center. The next energy level, you'll find two regions of high probability, and so on as your energy level goes up. So that's for a particle that's constrained by the potential. The energy levels are equally spaced, which is a very important thing. Another aspect to the solution, when you solve it and you get a wave function, is that you have a 0-point energy. You can't have no vibrations to a particle. And you can see again what's happening if you've got a particle that's constrained by potential. You are knowing you've got some degree of certainty as to where that particle is. And so from Heisenberg uncertainty, of course, you've got to have some uncertainty in its momentum. And so you can't have no vibrations at all. There always is a 0-point vibrational energy. Okay. Now, it's interesting that the energy levels are given by this expression. And this h bar omega is just to simplify things, that omega is related, the energy is related to the force constant of a spring, the spring force constant, and the mass of a particle. So just remember that the force constant and the mass of a particle are important in this constant you've got here. And your energy levels are nu plus a half, but these nus are whole numbers. So it's 0 plus a half is your first energy level, 1 plus a half of that, 2 plus a half, and so on. And you can see that if you have E0, if you put E0, the energy is a half h bar omega. So you can't have no energy. And then if you put nu as 1, you've got 1.5 times that. And then you can tell that the difference is h bar omega apart. They're a constant distance apart, where that omega is the k of the mass of the particle in that potential. Okay. But I think at the microscopic scale, it'd be very difficult getting a particle and attach it to a wall by a spring. Or maybe as a chemist, you might be able to find ways to do that. I'm more interested where you've got two particles attached together by a spring, because that, for me, is what I have in my mind as what a diatomic molecule looks like. So we're going to make some very minor adjustments to this whole situation for dealing with diatomic molecules. Important thing is that the energy is related to the force constant of that spring and the mass of a particle. That's the first thing. So that omega is, we need to know the force constant, the mass of a particle, and of course that the energy levels they go half, 1.5, 2.5, 3.5, 4.5 times that, so that the distance is equal in terms of energy between them. If we look at a diatomic molecule, now it's not a single particle constrained by a spring. It's two atoms that are working together. The maths works out much better if you have a reduced mass in it. And I mentioned reduced mass before, and I said we're going to come back to it again and again, and that it's better to work with a reduced mass, and rather than trying to find the center of mass with the two particles and how far they are. It's best to work with the reduced mass of the entire system. If you've got a diatomic molecule, you will know what the masses of your atoms are. If it's a carbon-12 atom, you know its mass. You can get its mass in kilograms. If it's oxygen-16, you know its mass in kilograms. You can put its mass in kilograms. If it's if it's carbon monoxide, you would know to put a carbon mass and an oxygen mass and get the reduced mass. You'd be able to calculate the reduced mass of the entire system. Because once you have the reduced mass of a system, the only thing that changes is that the omega term is now dependent on the reduced mass for the pair, instead of a single mass for the single particle. So for a diatomic molecule, this is what omega looks like. Omega is related to the force constant of a bond and the reduced mass of the diatomic system. And the energy levels are still going up from half is the lowest, then 1.5 and 2.5 and 3.5 and 4.5 times the square root of that. Okay. So important thing with the diatomic molecule, when you look at vibrations, there is a 0 point energy. And that 0 point energy is a half h bar omega. And that half h bar omega, well, the omega is related, is square root of the force constant for the bond over the reduced mass of the two atoms in that bond, the diatomic system. But your wave functions look like this. Your lowest energy wave function looks like that. So they will be at a certain distance apart. And then, of course, if you look at psi squared, you'll be able to see that at higher energy levels exactly what the situation looks like in terms of their location. Okay. But of course, remember from molecular mechanics that I said that an x squared potential does not really match a bond that well. So the question is, what what does a real bond look like? Does it really look like an x squared potential? The answer is no, it doesn't. So there's a problem. If you've got a harmonic potential, which is what we've looked at, you stick that into the Schrodinger wave equation, then you get these beautifully equally spaced levels. But of course, for a molecule, it might be more accurate to use a Morse potential, which is this interesting maths. So it'd be interesting what the Schrodinger wave equation would look like if you put this into the Schrodinger equation instead of that. And it seems bad enough over there. But if you put this in, the Schrodinger wave equation is going to be even more terrible. Of course, we do remember that from molecular mechanics, that the close to equilibrium, the harmonic and the Morse potential seem to have some kind of overlap that is good. I've got a question that's come through to me. And so before I go on, I want to just address it. It says, how does a vibrational motion depend on the reduced mass of the molecules? Okay, so I'm not going to go deeply into it, but what happens is that if you've got a single mass, that's easy because it's only one thing moving. If you've got two masses connected by a spring, both of those masses are going to move around the center of mass. So you could work with those two masses separately, but how do you combine them into a single calculation? And it works out. I'm not going to go deep into the derivation, but the maths becomes simple. All the terms become simple, and the algebra becomes simple if you simply work with the reduced mass. So the reduced mass is going to affect the vibration. So let me give you an example. So imagine if you had a heavy atom, I suppose, maybe a heavy halogen like iodine, and you had a small mass like hydrogen, then of course your reduced mass is going to be, when you have a look at the reduced mass, you've got 1 over a very small number plus 1. So 1 over a large number for iodine plus 1 over 1 for your hydrogen. And so your little term is going to dominate. And so it's going to be like having a small mass attached to a wall. Okay, so if your iodine is your wall and your hydrogen is there attached to it, you can see that in the limit, it's like having just the mass of a small one. Of course, if the masses are comparable to each other, then you've got the wall moving, and so you have to account for that. and the reduced mass is important. Has that answered the question that I got on the chat? So how does the vibrational motion depend on the reduced mass of molecules? And it's a way of simplifying the calculation. Right, so now the, yes, question? Yes, there was a question. Any questions? Okay, so reduced mass is a way of going from a single particle in a potential to two particles connected by a spring. And the maths works out really nicely. It's exactly the same, but of course you've got to have a reduced mass in the system. Right. Now the problem is that this x squared potential does not match perfectly the real case, even though we knew in molecular mechanics that the overlay around equilibrium is quite nice. So the problem is, if we were to stick that in the Schrodinger wave equation, we end up with an even more tricky situation. If you stick that horrible thing into the Schrodinger wave equation, and you solve the Schrodinger wave equation, you get your energy levels as being this horrible mess over here. And further than that, you'll see that the energy levels, they start off spaced together, but they start getting closer and closer and closer together. And those of you who did that iodine absorption prac will remember seeing diagrams with those energy levels getting closer and closer together, and exploring the levels and actually calculating the levels of the wells from that. And so that's an interesting result we get. But question is, how can we use the results of that we've got from for a diatomic molecule if we end up with such a complicated expression like this? We don't have a nice even spacing, even though we've got the energy levels. What we've got is the same term as before, but there's a term that is related to the anharmonicity of the system. This here becomes quite problematic. Just before we carry on, this is the real situation for a diatomic system. So you might think that if you've got atoms at equilibrium, you might need to pull the atoms all the way to get them to break. You might need to put this energy from the bottom to the top into a system to get them to break. You might think that this, from right on the bottom to right at the top, as being the dissociation energy, and it's not. Because remember, you can't have no vibration energy. You always got a 0 point. A molecule will never be at the bottom of the energy. They'll always be at the first energy level. So that makes it interesting because you actually have to put less energy to break a bond than you would expect. And the less energy is because it already has some energy. It's 0 point energy. And then you can pull it out of a well like that. But now we need to address this problem. How can we use this and apply this to real molecules when its situation is so much more complex than what we had with the harmonic, with the nice, beautifully spaced energy levels? And the answer is quite simple, is that right at the bottom of the energy well, this matches the other situation quite well. It matches the x squared very well right at the bottom. And if you look at a molecule like carbon monoxide, we might want to use Boltzmann to say, well, if you've got 1,000 carbon monoxide molecules, where are they all? Are they at energy? Are they spread out between energy level 0 and 1 and 2 and 3? Well, for carbon monoxide, at room temperature, the energy level 1 is about 12 times Boltzmann's constant times 298 Kelvin. It's about 12 times kT. If you put that as an energy, you'll get the exact difference in energy between energy level 0 and energy level 1. But I've expressed it as 12 kT so that we can go to Boltzmann and work quite nicely. Because if you take 12 kT as being that energy, the difference in energy, and you put 12 kT up there, I think that, just check my Boltzmann. You put 12 kT and you divide it by kT, you end up with the fraction in energy level 1 over the fraction in energy level naught as being this really small number, meaning that if you've got 1,000 carbon monoxides here, you've essentially got no carbon monoxides in energy level 1. And if you've got none there, there'll certainly be none in energy level 2 and energy level 3, etc. Which means that if you did some spectroscopy on this, the absorption would be, the maximum absorption would be from 0 to 1. So there's a selection rule that says it can only jump 1. And so the change would only be there. And this part matches really well the bottom of the this place. So you can see the bottom here matches very well here. Those two energies match, and up here it doesn't match at all. However, with carbon monoxide, we find they're all at the bottom, and when you do spectroscopy, they're going to jump up to number 1. So they're not going to jump up into those other parts when you do vibrational spectroscopy. So we can just view the diatomic molecule as being something like this, where it's jumping from energy level 0 to energy level number 1, which is fine. So we can use this delta E is equal to H omega. Remember that omega is dependent on the force constant and the reduced mass of the system. So for diatomics, we only see the jump from level 0 to 1, and it's where they match well with the harmonic, and so we can use this lovely spacing. I'm going to go back. We can use this lovely spacing that we've got between energy levels, because we're right down here to work things out. Okay, so if that spacing is that beautiful spacing h bar omega, that was that constant spacing in the harmonic potential, it might be nice now, because when you do vibrational spectroscopy, you often work with wave numbers, is how can we relate this back to a wave number? Well, a wave number is 1 over lambda, and if you put C as lambda nu and E equals h nu, you can get that 1 over lambda is E over hc, but we know what E is. It's h bar omega. So let's put h bar omega in the E, and we've got hc at the bottom. You end up with the fundamental vibration wave number as being this omega over 2 pi c. And of course, don't forget what we had omega is. If you put that omega back into it, you get that fundamental vibration is 1 over 2 pi c k over the reduced mass, which is really nice. Now, I want to tell you the significance of this, because we can take a diatomic molecule and take it to the spectrometer, and we can measure the wave number that's coming off from it. We can measure that fundamental vibration as a wave number. So if we measure it and we get a wave number from it, let's see what else we can find. These are all constants. 1 over 2 pi c is constant. What about the reduced mass? Oh, we'll know what molecule we're putting in. If it's carbon monoxide, we know it's carbon monoxide, and we know the bond distance for a carbon monoxide. We know what reduced mass is. So we don't need bond distance. We know what the reduced mass is of carbon monoxide, so we can put that in. So what don't we know in this? The only thing we don't know is what K is. And is K useful to us in any way? Have we, what would be the point of finding K, the force constant for a bond? Anyone? Well, the point is, go back to molecular mechanics. Yes, yes.
I was going to say, for all our calculations with E bend and E stretch, surely we have to know that constant.
Absolutely. So that's a very interesting case, is that we can use quantum mechanics to find out what the K we need is for the molecular mechanics. So that's really interesting. That K is very important to us. And of course, mu, don't forget that if you've got a diatomic, you just need to know the mass of the two particles to calculate mu. And we can, from experiment, if you get mu naught, then we can work our way back to find what K is. Okay, so can I just summarize where we've come through in this lecture? Problem is that we've gone from a case where the potential is naught to where we've got a harmonic potential, we've got a spring in action, and that changes the Schrodinger wave equation from having a naught, which is really nice, to having a more complicated expression. And of course, I'm not going through the solution of it, but the solution to this particular version of a Schrodinger wave equation, when you find the wave functions and the eigenfunctions, you find that the energy levels are equally spaced. And the difference between the energy levels is proportional to the force constant over the mass of the particle. When we go to a diatomic system, to maintain the same, the mass works out almost exactly, almost precisely. Well, it works out precisely if you exchange the mass for the reduced mass of the entire system. If you've got the reduced mass of the entire system, then your energy levels come out exactly the same. And of course, the omega term is K over the reduced mass. So this is great in terms of a diatomic molecule, except that we realize as chemists that the diatomic molecule is not a harmonic potential. It is rather a Morse potential. And the solution to the Schrodinger wave equation, where you stick a complicated potential to the Morse potential into it, shows that the solutions have those energy levels moving close together. However, we find that from the Boltzmann distribution at normal temperatures, that molecules really only they're only sitting at that lowest vibrational energy level. They don't have enough energy at room temperature to be populating the higher energy levels. Further, when you do spectroscopy on them, they only jump one level. So we only need to be looking at the bottom of this Morse potential, which is really very similar to this harmonic potential, where the energy difference is simply h bar omega apart. So we can solve that problem. Okay, and if the energy difference is h bar omega apart, we can convert that to a wave number. And so the wave number is also dependent on omega, but we don't forget what we had omega to be. And so we'll end up with the wave number over here. Okay, so the question is, are they in low energy levels because there are no pi electrons? Okay, so just be careful because what we're speaking of here is not an electronic energy at all. So this here is an energy that is contained, it's an energy due to the bond between two atoms. So if you look at a diatomic system as a whole, and we're looking at the vibrations of that diatomic system. So I'm not even considering electrons. The low energy levels are from the Boltzmann distribution because at normal temperatures, there's a lot of energy floating around, but is that energy enough to make sure that some of your molecules are vibrating faster at higher energy levels than others? It's perhaps not, because the Boltzmann distribution has said that most of them are sitting, most of our molecules in our sample of carbon monoxide are sitting in the lowest vibrational energy level. Okay, does that answer the question?
Yes, thank you.
Okay. So that's where I want to stop for today. Okay. So please have a look at this. The result of this is really it's absolutely crucial, and you see the connection between molecular mechanics and the QM stuff we're doing. So it's absolutely crucial because we can now take some examples and work our way back to calculate K for a system. Okay, so please, two things. Have a look at the QM notes that I've provided, Please also look at my annotated slides and also come back to the um, lecture videos if necessary. Okay. Any questions on today's lecture? Okay. As always, I have my emails open, and so any problems you have, please contact me, and I will try and respond as quickly as possible. And if there's anything you want me to address in class as well, let me know, and I can take some time for class to address any issues you may be having. Okay. If there are no further comments or questions, anything further, then I'll see you on Monday. We'll chat on Monday, same time at 11 o'clock. Thank you.